I'm Andy, and this is Sanket. And today we're going to be talking about productionizing Python ML models with Fusion 5. So we're just going to talk a little bit about what we've built, and then we're going to try to show it in action. So I'll talk a little bit about how it was built and the motivation behind it. So for Fusion, one of its biggest selling points is the out-of-the-box experience that you get with ML and AI, especially if you're a search developer that doesn't know a ton about data science or a ton about machine learning and training models. We offer a really good experience for search developers that just want to plug in different components and capabilities that we've built, like NLP, signals, recommenders, and be able to kind of stitch everything together into a search application. But if you're a data scientist, chances are you probably don't want that out-of-the-box experience because you already have just all the tools that you want to use. And also, you need the power and flexibility to be able to take your data really seriously and use Jupyter and train your models and get all of that stuff working. So you probably have a bunch of models that you already have trained. They're really accurate. And what you really want to do is just be able to just plug that straight into Fusion or plug that into a search application with pretty smooth integration points. Up to this point, like our story for integrating custom models hasn't been terrific. So, we haven't had a lot of really smooth ways of doing that. And, there's been a lot of friction in integrating models, whether it's like, oh, okay, if you have a Python model, you've got to, wrap that in a server. And, we have this stage where we can call it to that server. So that's not a great solution. And, one of the reasons behind that is because Fusion runs on the JVM, and we've handled mostly JVM models like Spark ML and MLeap, OpenNLP. So we got this question all the time, like, can I use my own, spacey model with Fusion, or XGBoost? I trained a Keras question answering model with Fusion, or I trained, a sentiment model with TensorFlow. So can I plug this in and use it with Fusion? I'm an expert user. I don't want the out-of-the-box stuff. I want to be able to just kind of plug that in. So I'm happy to say that with the 5.0 release of Fusion, the answer is yes. So what we're offering is real-time ML model serving using native Python. And again, it's for data scientists who want to integrate custom-trained Python machine learning models with Fusion's index and query pipelines. So with native support for Python models, we've closed the loop and are able to cater to both the search developer and the data scientist, offering a powerful data platform for building AI-powered search applications. So just to kind of wrap everything up, we offer fully integrated access to your Solr collections, which you can use for training models. Now you can BYOM, or bring your own model. I'm not sure if that's a thing, but you heard it here first. We still offer out-of-the-box ML training models for the folks that want that kind of low-code experience. And Fusion just brings all these components together so you can create a scalable search solution with fully operational pipelines. So let's talk a little bit about the architecture of the system. So what we have built is a Python model execution microservice, which is fully integrated with Fusion 5.0 running in Kubernetes. So there are two main components. There's a JVM component, and the JVM component handles the same models that we handled in 4.2, which is Spark ML, MLeap, OpenNLP. And it handles a lot of kind of like the bookkeeping and sort of like the internal model lifecycle management stuff. And then running alongside it is a Python component that handles, so this is native Python, and this component is responsible for all of the Keras, TensorFlow, all that stuff that you would want to plug into Fusion. So the service exposes a few simple API endpoints. So things like CRUD operations, so you can add, update, and delete user-defined models. And of course, the main API method is running predictions. And we're also offering a data science integration toolkit, which includes client libraries, which hopefully makes everything a lot easier to use. So you can see on the left side, there's some code there. This is taken from a Jupyter notebook. And the hope here is that as a data scientist, Fusion can offer all the data platform for you to do your work, and you could do everything in Jupyter. So within Jupyter, you can load all your data and suck your data out of a solar collection into a data frame. And from there, you could do your modeling with whatever library you want to use. And then you can interact with this client library to just deploy your model to Fusion, test it, make sure that it works correctly. And once you've done that, once you've deployed your model, it is fully accessible by our query and index pipelines. And these query pipelines actually, or these query index pipelines, call out to the ML service over gRPC, which, if you're not familiar, it's an RPC library developed by Google, which is it's really performant and scalable, used a lot for microservice microservice architectures. And then, as far as these stages go, Sanket will demonstrate how all this stuff works and everything. And lastly, when building the service, we had a few important goals in mind. So first of all, we wanted it to be extensible. So we're offering a pluggable API for data scientists to add data processing and modeling code. Second of all, it has to be scalable. So we're leveraging modern technologies like gRPC and Kubernetes for performance at scale. So the nice thing about being cloud native and running in Kubernetes is that you get a lot of things for free, like high availability, auto scaling, and all these things. So say you're running a batch process that's calling out to the ML service a lot. What Kubernetes can do is it can scale up that service and add replicas on demand, and scale that back down whenever it's not being used anymore. So you get all that nice stuff for free. Third, we want it to be flexible. So the API that you would have to implement supports a lot of different kinds of machine learning models. So one of the challenges of building kind of like this pluggable architecture is that we need to be able to handle the wide variety of different machine learning models that are out there. And these machine learning models have different inputs and outputs. You can have a classification model that takes in a bunch of text and returns, a numeric score and, a textual category. But you'll have another machine learning model that takes in, a bunch of different kinds of numeric fields and spits out, a vector of numbers. And so, depending on what kind of machine learning task you're trying to complete, these inputs and outputs are going to differ, but I think we offer a pretty simple way of accommodating all these different various inputs and outputs. Again, it's integrated, so it's fully integrated with Fusion's index and query pipelines. Once you install Fusion 5.0, there's nothing additional you have to install. It's just kind of there. The microservice is running. You can start using it right away. And lastly, we wanted to make this as easy as possible. So it's API driven. It has convenient client libraries. We're offering the toolkit to go along with this thing. So right now, Sanket's going to go and show it in action.
Thanks, Andy. What I'm going to do is I'm going to try to show you the process of actually taking a machine learning model, building it, and then trying to integrate it in Fusion and running it through an index pipeline and to see it in action. We wanted to keep the process of actually taking a model and putting it inside Fusion as simple as possible. We wanted the ML engineers and the data scientists to focus on building quality models. And once they have a good quality model, we want it to be very easy to take that model and put it into production. And when if you have worked with machine learning models, it's really hard to actually get a good quality model. There are many iterations involved. There are many architectures that you have to try out. There are different error functions, matrix. You need to validate your models. You need to validate your data. You need to look for biases. There are a lot of things that go into actually building a good quality model. Now, once you have that model, it's not fun to actually struggle to use that model in production. And to ease that thing, we have come up with this 4-step process where you take a model, train it outside Fusion, wherever you want, or Fusion can train that model for you. Then you create a plugin or a bundle, which is nothing but a zip file containing all your models, your tokenizers, your serializable objects, your custom code, and then you create a zip file which is called as a bundle or a plugin in Fusion. Then you take that and deploy it to Fusion and test it out, how the predictions are working. And once you're satisfied with that, you integrate it with your query and index pipelines. And this process is built keeping the data scientists and machine learning engineers in mind so that anyone with decent Python skills should be very easily be able to take this and put it into production. And we do understand that not always data scientists are going to put things in production. There is a process in place where you have to give it to your DevOps teams who will take care of that. So it's also API driven so that you can put it in your Jenkins pipelines or your Ansible scripts or Chef scripts, what you have. When you're training the model, we want our users to have complete control over it. And many times, out-of-the-box solutions are not sufficient for the domain-specific data that you might have. Sometimes you need domain experts to train those models using specific knowledge that our out-of-the-box jobs might not have. Sometimes there is critical data, sensitive data about the users that you cannot really bring into a search application and train the models in that environment. It has to be in a very protected environment where you train your models. So for those cases, you will definitely want to train them outside of Fusion. And then data scientists sometimes just want to do their own thing, no matter how good solution you offer it to them. And I'm a data scientist, so I always love poking around models and really trying to get the best versions out of them. And for that, what we offer is we offer integration points. And to train the model, let's say your data is in cloud or in local disk anywhere, you can easily connect it to Jupyter and then bring the data in and train your models. If your data is in Fusion already, you can still get it out. We offer connections to Fusion Solar via our own connectors so that the data in Solar is also available for you in your training environments to build your models. If you already have a Spark cluster, you can leverage that. If not, if you can leverage the Fusion Spark cluster, you can connect to that and use that for your training environments. And there will be, again, many iterations around developing the model. And once you have a good version of the model, you're satisfied, what you have to do is you have to just serialize those objects and bring them to the disk. Typically, if you're training a deep learning model, it's going to be a model. There will be a tokenizer. And then if you're using some pre-trained embeddings, you'll also want to export them. Once you have those things exported out, all you have to do is create a bundle file or a zip file. And what it should contain is all your serialized object files that are required for the model to give predictions, your custom code, and then a special file called predict.py. And that file is executed by the ML service whenever it loads up. Now it has the logic to actually do the predictions based on your model. So it should have two functions at the very least. First is the init function. What that init function is going to do is you have to just write how do you want to load the objects that are serialized to disk. How do you want to load your model? How do you want to load your tokenizer, etc. And that will happen only once when the service starts up and the model is loaded. Next is the predict function, which will take in a dictionary of input and return back a dictionary of the outputs. And this predict function is necessary to generate predictions for single input that the model will receive. So after the model is loaded, every time you ask for the prediction, this function gets called and the service will return back whatever dictionary you're returning from there. Next, once you have your plugin ready, when the zip file is ready, you have to actually test it and put it onto Fusion. So we are building a Lucidworks ML SDK, machine learning SDK, where it's going to be very easy for you to actually go and connect to your Fusion instance, right? What we want to do is keep it very simple for the data scientist to actually go and test it out. So you can do it via pip install. So if you do pip install Lucidworks ML SDK, you will have this connection point to use. So all you have to do is specify the model ID, the app name, the Fusion app where this model should go into, and the Fusion URL wherever your URL is, or like the dev environment or the QA environment where you want this to be tested out. And then with that, you just specify which model you want to upload. So you specify the zip file, the location of the zip file where it is. Let's say it's on my laptop right now, so I specify that location, and the client is already set up to use the Fusion URL or connect to Fusion. Once that's set up, you simply do client.upload model, and that model is immediately going to go and transfer it to your Fusion instance. And the Fusion ML service, as soon as it gets this model from your local machine, it will immediately spin it up, call the init function, and be ready to serve predictions. Once we have done that, what you have to do is you have to test it out. Am I getting the expected results out? Once I put that inside Fusion, do I really know that it's functioning or not? So we offer a predict function on the client. Well, it's going to be a simulation of what the index pipeline would do, just without going through the process of actually building a pipeline and anything like that. So just focusing on the machine learning model, you do a prediction on the pipeline, prediction on the model, so that you pass in your model ID and the input what you want to process, it will give you back some results. So in this case, what you see on the last part of the image is, it's a sentiment analysis model. You pass in the input text and it will give you back the sentiment and the score. If the data looks good, the structures look good, we are good to go. It means that the model is running in Fusion 5. Now, as a data scientist, I would use the ML SDK. It's very easy to get on Jupyter Notebooks and then deploy them. But if you are going to have to actually hand it over to someone else, like the DevOps teams, then you want to use the API, which you can integrate with your Jenkins to push the models into your Fusion collection, or you can put it in your Ansible scripts or Chef scripts based on the architecture that you are having in your own organization. Once we are confident that our model is running good inside Fusion, we have to create a stage to integrate it, because we want to consume the model into your index pipeline for indexing or enriching your documents, or maybe at the query time to process the incoming queries. Maybe it's a query classifier or facet predictor, something like that. In the machine learning stage, you have to do three things. One is specifying the model ID, what model should be used. Then you have to put in a transformation script for the input. Basically, you just say, here is my document, it has 7 fields in it, which field should I use and how should I pass it on to the machine learning model? What is my model expecting? Based on that, you will fill out these things. Then the model is going to return back some output. You have to say, what are the field names? Do you want to rename the fields that the model is returning back? These are going to be very straightforward and simple few lines of JavaScript code, which everyone should be comfortable with. Let's take an example of the document here. We have a document which has a few fields, the user ID, title, text, etc. What you want to do is, this document is going to flow through your index pipeline through the JavaScript stages. In JavaScript stage, you create a hash map, and then you pass in that document.get first field value, the text field. So this text part that you see here is going to be stored in the model input as in that hash map as input, and that will be this hash map will be passed on to your model in the machine learning stages. Now remember, if you remember that the predict function will take in a dictionary as the input. There is a translation that we have to do between the Java objects versus the Python object. So this is that connection point where you create a hash map and it will be treated as a dictionary in your Python, in the Python world, in the predict function there. So the model gets the input, which is like having issues about something. What it does is, it will go and call out to through the gRPC interface, it will go to the models that we have running. It will execute its prediction and send back the output. The model has created this output called sentiment, it's negative, and the score is 0.49 something. Now what we want to do is, let's say these are the fields that the model is returning back. We want to convert them into something that Fusion can use or the documents can be leveraged with, or annotate the documents. What we do is, we simply do a document.add field, and then sentiment underscore s is the field that we want. So model output.get sentiment. So model output is, again, it's an hash map of the object where all the output from the machine learning model will be stored. You simply have to pull it out and pass it on to your document. Now what you see is, in this whole process, You have to just write in the input parameters, the output processing types, and you pass in your input document. It will be automatically attached with the additional metadata that you have. Hopefully this is clear. Now we'll go into a demo and actually see one of the classifiers that we were building on. Okay, give me a second. I need to change the display preferences. Actually, never mind. Okay, I'm going to talk about one of the classifiers that we were working on. So it's a toxic classifier, toxic comment, or the data that has curse words used in it or bad language used in it. We want to flag that. And it's actually a very common use case in search. If you have a chat portal or a public discussion forum in your organization, whenever comments are flowing in, you want to flag them through this classifier. The second very popular use case is when you are doing autocomplete, auto-suggest, or related queries. And if you have your query catalog, if you look at them, sometimes there are queries that you don't want the user to be suggested. So you don't want to suggest bad queries to the user. So this kind of a classifier can be used on the search side as well as the indexing side. And to build the demo around this, what we use is the Kaggle competition data around the toxic classifier. And that data has about 160,000 comments in it, out of which only 50,000 are toxic comments, and the rest of them are non-toxic. So it's a very highly imbalanced data set. So we are going to actually show you here what the process of actually building a classifier would be for a data scientist. We load the data in and we check what the distribution of the data is, and then we find out that, okay, well, it's a highly imbalanced data. So there are two ways you can do it. You can adjust the imbalance, or you can create a completely balanced data set by downsampling your majority class, which is the non-toxic comments. Through our experiments, what we have found out is that 3:1 ratio actually works well, because the model is kind of learning the prior probabilities of the distribution that it would see in the real world. In the real world data, this distribution will follow, and the model will be able to adjust according to that. And we do our own thing. We basically create a training data set. We downsample it. So we have 45,000 non-toxic comments, 15,000 toxic comments. And based on that, we use the Keras tokenizer, a simple tokenizer, and then we load the data, use the same tokenizer to load the test data for that. Once we have that, we define our model. In our model, we use focal loss, which is allowing our model to actually focus on the predictions that it has made mistakes on. So every iteration, it gets a higher penalty for making the same mistake again and again. So we use this focal loss, which kind of allows the model to focus on certain predictions that it's doing wrong consistently. Then we use some early checkpoints and early stopping criteria that we don't want our model to be overfitted. So any version that's the best one, we save it to disk. And we use an embeddings layer. We are learning our embeddings from scratch. You can also use pre-trained embeddings, but we want to keep our model size small and nice. So we learn our own embeddings here. Then we do a dropout to adjust for overfitting and use a bidirectional LSTM layer. So LSTM layer allows our model to look at the text before it and after it and make a judgment based on that. It's a sequence modeling thing. After that, we use attention layer. Attention layer is a new layer that has kind of like come up in the recent time. What it allows us to do is take this model and understand what is the key portion of your text that it is looking at when it's making certain kinds of predictions. And to do that, we actually use Keras building blocks. And then we have the model, we have defined the model, how do we want to optimize it, what are the metrics and the optimizer. Once you have your process written, here is the image that will show you what that model looks like. It has an input layer, embeddings, dropout, bidirectional LSTM. And after that, what you're seeing is just the functional building blocks of the attention layer. So we are using Keras blocks. We don't have to actually write some custom code for that. Using that, then finally we come out to the batch normalization. And then we use a dense layer to just convert all the numerical things that we have into predictions and use a sigmoid for getting a probabilistic distribution around that. And then we train our model for a few epochs. It very easily overfits, so we control that very rigorously. And then we test the performance on our test data set. Once we have that model ready, we kind of go through the confusion matrix, and let's say we are satisfied with this model for the round 1 that we have. So it has a 90% recall on actually predicting the toxic classifiers. toxic comments out here. So we are good to go with this. Now once we are good to go with this model, what we do is we kind of save it. So you save it to disk, you save the tokenizer to disk, and once you do that, you create a folder. I have a folder called models. We are working on a lot of models here, so we are going to only put the toxic classifier out there. So you bring in your toxic model, which is the Keras model or the TensorFlow model you might have, and also the tokenizer that we need. And then you create this special function called predict.py, which has your prediction logic in it. So in predict.py, you have some standard import statements, and then you'll define your custom objects that you might have used during the training process as you need them for the testing also. In the init function, what you have to do is simply load the model. We are using load model, and this is the model name that we want to load and some of the custom objects that we might have. And then for attention model, what we do is we split the model and pick out one of the layers to just get that focus of the model when it's kind of doing the prediction. And then we also load the tokenizer that we will need. So we load the tokenizer through pickle, and this will happen only once. For every prediction, the predict function will get called. It will get x as an input. It will check for the input if it's valid or not. Once it's valid, we are using the tokenizer to convert it to sequences, pad the sequences, and actually do a prediction on top of it. So once you predict it, we are going to create a label for it. If the probability is more than 50%, call it toxic, else non-toxic. And then we do the attention, use the attention model, which is a subset of your actually big model that you have. And we do some post-processing on the result outputs. We try to rescale the data. Optional steps, completely dependent on your domain, on your data, whether you need to do it or not. So finally, what's important is what is this returning? It returns a dictionary which contains a label, a score, and the attention tokens in it. So you're ready with the predict.function now, predict.py file with the prediction functions. You want to now take this thing, this whole bundle that you have, and put it into Fusion. For that, your toxic classifier model is going to look like something like this, where it has the pickle files, the h5 files, and the predict functions. And then to deploy it to Fusion, you're actually going to simply create a zip file out of it. So we have the toxic classifier, and then we are creating a bundle called toxic classifier.zip. We're creating a bundle out of it. And before we actually even go and test it inside Fusion, what we want to do is test it locally. So in the ML SDK, we also provide a local bundle runner, and you just provide the zip file path wherever your model is, take that thing and run it locally. So it will do the same thing. It will load the init function and be ready to serve your predictions. And you can do runner.predict, pass in the input, and it will tell you it's toxic. And it will also tell you why it is toxic or what are the keywords that it was paying attention to. Then you take it and deploy it to Fusion. So to deploy it to Fusion, you create a client, establish the connection, pass in the parameters like your URL for the API wherever your Fusion server is running, pass in the app name, username, and password for it. And then you simply call client.upload model, whatever your bundle zip file, wherever the location is, and the model ID for it. Now when you do that, it will load the model and push it inside Fusion. We did this beforehand just because we don't want the variability of the network, and the model is about 40 MB. So it will take time to load if it's right now. Then to check if the model was loaded or not, or what are the models that are available in this Fusion server, you do client.list models. And then you'll know what are the models that are available. So we have Python model called Spacey, toxic classifier, OpenNLP, and then sentiment analysis model. There will be, if you are pushing multiple models, you will have all of them listed down here. Then the final step is you want to actually test the prediction. Given this thing, that it's working or not inside Fusion is really important. It worked locally. We want to see the same behavior on the Fusion server. So you call the client's predict function. So earlier what we did was it was the local runner's predict function, which was running locally on your machine. But now you call the client's predict function, pass in the model ID, pass in the input text, and it will return back the score, label, and the attention tokens for you. And that's it. Now you're ready with step 3. Step 3 is successful here. So what we have to do is now we have to go to Fusion, right? Because that's where it will be leveraged and consumed. In Fusion, we are going to okay. It's always a network thing, you know. Yeah, so in this app, whenever it loads up, what we are going to see is we have a CSV file in the blob store, and then we have a data source job and an index pipeline attached to it, which has connections to the ML model service and the configurations that will come back and forth. I just have to wait for this to come up now. Yeah. Okay, never mind. Something's coming up. Okay, so right now I already indexed the documents, so let me just clear this collection. And let's look at the blob store real quick. In the files, we have this sample file, which has about 22 documents in it. And looking at the index workbench, we load this data source here. And let me disable the models first. So what you're seeing here is, right now, you have this ML toxic classifier stage. Without this stage, what you can, let me zoom it a little bit. So what you're seeing here is the comment underscore text underscore t. So that's a field that's coming from our CSV file. So it has many fields in it. And this is the important field. Based on this, we are going to pass it to the model to make the predictions here. And then what you're seeing is the CSV parsers and everything is working. Now you want to look at the machine learning stage. You want to set up that stage. So you create a stage called machine learning, pass in your model ID, that's toxic classifier, and then the input fields parameters that you need. What we are doing here is simply creating a hash map that we saw earlier in the presentation, and doc.get first field value comment underscore text underscore t, which is coming from the document itself. And that is being passed on to the model down there. And then when the model is coming back to us with predictions like the label, the score, and the attention token. So we are doing model output.get and assign it to the document as toxic label underscore s. Take the score and assign it as toxic probability underscore d. So Solr can actually index them based on the field types that we have. Take the attention tokens, it's a multi-valued field, so we put an underscore ss to that so that we can facet on it or search on it or highlight them. Once you have that, all you have to do is save that thing and then enable the pipeline stage. And now you see that it's actually, right now it's like on real time, it's going to the model, passing the input text, getting out the predictions and then transforming them and adding them as specific fields to your document. So you get the attention tokens underscore ss or the toxic probability and the label that you have. So I'm going to save this and start the job. It should take about 30 seconds. And once we have that, we should have about 22 documents in the collection. Okay, that was quick. Yeah, so we have 22 documents here, which have been indexed. So let's look at the documents. So we have some documents here which have just come from the CSV, went through this whole pipeline and were indexed into Fusion with the specific labels there. So we create a facet on this. If you want to look at the toxic ones, it tells you what is, and then we are also showing the field called attention tokens underscore ss, which tells you why this particular thing was flagged. So dear God, this site is horrible. So the model is paying attention at horrible and site. So idiotic, arrogant, and mentally retarded. So all these things kind of trigger the model to actually tell you why it flagged something as toxic or why is it non-toxic. And these kinds of models are actually very important, especially in the government domain or in the finance domain, where you cannot use models that cannot be explained. So governance and compliance is very important. But now deep learning is becoming so powerful that it's inevitable that you stick to deep learning. You cannot keep on using the older methods that you have. So to leverage this, we are trying, now attempts are being made in the research community to actually make these models more interpretable. So the image models that are now you find online, or you can check on some of the research papers, they'll show you how the models are like kind of being decoded at each step about what portions of the image they are looking at. So on the NLP side, this attention layers provide similar kind of functionality to us to actually understand what's going on with our model and what kind of predictions it's making, why is it making that. And that's it for the demo. So you have all the models available that Fusion is, like Lucidworks will be using this, our own library now in the future to actually deploy these models. So what experience our clients are going to have or our users are going to have, it's the same experience that we as data scientists in Lucidworks are going to have. And we have a GitHub project which will be highlighted here. So if you want to try out this, Fusion 5 has been released now, and we have a GitHub project to actually go through the whole steps and processes. So you can look at the notebooks. They are published on this project and you can download them. You can install the ML SDK and play around with it. And you should have access to it because it's a public repo. So thank you very much. And any questions you might have, feel free to ask them. You mean Fusion? Yeah, no, Fusion is not on Kubernetes. Like I'm running it in Docker environment, so not a big thing because it's like a very small deployment. Yeah.
And for productionalizing,
Yeah.
would you can run the model portion or API portion in Kubernetes and the
Oh yes.
will be still on old style, or
No, everything like Fusion 5, I think everything is like in Kubernetes, right?
Yeah, so right now, for Fusion 5, everything would
You want to use them?
everything would be running in Kubernetes. So all the microservices, including Solar, Zookeeper, all that stuff, be running in Kube.
So it will be auto scalable and everything based on the policy that you have. You can scale these machine learning pods. Yeah.
This presentation is very impressive. I like the part especially with the demo. You walk through the step by step, like how do you, utilize, machine learning part. My question is this presentation deck available for download?
It will be on YouTube, I think. So
Yeah,
the
within
record-
about 2
yeah.
weeks, I think. It should
Within
be
2
up
weeks,
on-
it should all be on YouTube and slide share, I think.
Yeah, this is all being filmed. You'll have slides and everything too.
Yeah. Yeah, sure. Yeah.
Mm-hmm. Have any NLP-based models for intent modeling? And what I specifically mean by that is so I'm from in the leisure space. One of the things we struggle a lot is really to model the intent of NLP phrases, basically, right? So can you comment on that?
Yeah, so Fusion 5 is going to come with 3 models out of the box. So one is a sentiment model that we have trained internally. And then Spacey is another model. So it's an NLP model for modeling on Python. And then we have an open NLP model as well. So there's nothing you need to do to get that running. It's all preloaded. You don't have to even interact with the client. We have stages that interact with those particular models so that you can take text, annotate it in Spacey, and do things like, hey, I want to index all the entities in a separate field, and you could do that all through the index pipelines.
Yeah.
That is going to supply the data to train it.
Yeah, if you have custom entities, then yeah, you'll have to train that model and just bring that model in. But if those are entities like specific time portions that you are looking into the data, in that case, it's pre-trained models. You don't have to actually even train them. You just have to pass in the data through the index pipeline and they'll work out.
But how do you know the intent without us supplying the context? Like from in our domain, there's a specific context to a phrase. For example, I want to go to a place, or let me make it. Like I want to be in a place with a lot of sun. Right? So there is a specific intent for a user coming on Merit.com, for example, for that phrase, which is going to be different if you are probably at another industry. So how do you capture that intent without any context from us?
No, so that's what I'm saying. So if if the intent is about getting specific information from the text, which the models have already been trained on, like getting the location that the person is looking for, or who is he looking, yeah. So the pre-trained, there are some tags that already the models know how to get them. If that's the case, then you don't have to train them. But in your case, when you have these, if you have a feedback loop, if you capture the signals, the indications that are happening on your website based on the click stream behavior or anything like that, Fusion can actually do aggregations on top of it and understand the behavior and use that aggregation data to actually train a model. Yeah.
But basically, you have one of these models that suffice what you just mentioned.
Yes, but we will have to, for your specific domain, we have to take a look at the data actually and then make a recommendation whether this will work, or do we have to actually train a new one for you. Yeah.
Thank you.
Uh-huh. Yeah. Yeah. Yes.
Do we have any manifestation of the Python environment itself? Or libraries, dependencies, or what's that? Yeah, I'll speak to that. So the ML surface ships with a bunch of dependencies out of the box, and all of that list is available in the GitHub repo. So the toolkit actually includes the libraries, the requirements.txt, so that you can sync up your local environment with what's currently installed in the ML service. And it includes a good swath of the most popular machine learning libraries out there. If you absolutely need more than that, you can extend the base image. So we have all the images published on Docker Hub, and you can extend the image, add the additional commands that you need to add whatever you want on the image. It doesn't even have to be dependencies. It could be just, I don't know, you have pre-trained embeddings that you want to slap in there. Like, you can do that. But it is an extra step, so you have to extend the image and then make the image available to your ops team to deploy your kind of extended version of that image.
Yep.
You said that using Fusion 5, we should be training our models outside of Fusion and then importing them into Fusion. Then later on, you said you could train them in Fusion.
Yes. So Fusion already has random forest and logistic regression classification training modules. If your data already resides inside Fusion, then and you want to use the Fusion models, right? Then you can just use the out-of-the-box stuff, and basically it's a UI, guided UI, click button, and you'll have the model ready to use. So this case is more applicable when you want to do something more. You want to get more data, or you want to train something outside. You want to train a deep learning classifier or things like that. Yeah. So if you don't want to do that, you can use the out-of-the-box stuff. It's always available for you.
So if we have all our signals in Fusion already,
Yes.
we can do the training there.
Yeah, Fusion can do the training for you too on specific data sets. The way you model the data, the input, the output, it can train a classifier for you. Yeah.
I have a question about configuration management. Basically what this is, you're creating an on-ramp for merging data science workflows with search engineering workflows, which is great. But it's also two very different workflows with different tempos. So like once you start going down the path of machine learning, it's all about incremental improvement and shipping as soon as you see that, right? So I don't think Fusion is taking any responsibility for sort of model provenance or version control or understanding any of this stuff at this point. But is that something you're looking to do in the future, so you can actually sort of look at the lineage of your configuration and understand what's running where and where it came from and when? Now it's not just let's say an index analysis changes that are less frequent happening. Now there's going to be more frequent retraining workflows coming on and affecting what's happening in your index. If that makes sense.
Yeah, I mean, that's a great point. That's something that is definitely on the roadmap of where we want to go with this. Right now, when you're adding and updating models, there's no versioning of any kind or anything like that. It's just pretty much a name. So if you wanted to add another model with a different version, you just give it a different name. But obviously, that's not ideal. So So yeah, I think in the future where we want to go is kind of like a more intelligent repository of models where it does do semblance of version control, keeping track of, perhaps some statistics about the model and all those things that you'll want to kind of keep track and make sure that the right models are there and you know what happened.
Cool. Thank you very much.
Thank you very much.